quantum electrodynamics eventually provided a framework that resolved these issues through renormalization and deeper structure. Similarly, in classical descriptions of atoms, electrons spiraling into nuclei would produce singular behavior. The atom should collapse instantly. It does not. Quantum mechanics replaced that picture with one that eliminated the singularity entirely. The infinities disappeared not because reality was infinite, but because the description had changed. From this perspective, the singularity associated with the Big Bang looks less like a physical beginning and more like a placeholder for new physics. Most physicists interpret it this way. They do not believe the universe literally reached infinite density. They believe our equations stopped making sense. This raises an important question. If the singularity is not real, then what replaces it? What actually happened when the universe was extremely young? The honest answer is that we do not yet know. There is no complete, experimentally confirmed theory of quantum gravity. There is no framework that successfully combines the smooth geometry of space-time with the probabilistic nature of quantum mechanics in a way that has been tested under cosmological conditions. Without such a theory, any description of the earliest moments remains speculative. Several approaches exist. String theory suggests that fundamental objects are not points, but extended entities, which could smooth out infinities. Loop quantum gravity proposes that space itself is quantized, made of discrete units that prevent infinite compression. Other approaches explore causal sets, emergent space-time, or entirely new mathematical structures. Each of these ideas offers ways to avoid singularities. In many of them, the Big Bang singularity is replaced by a bounce, a transition, or a phase change. The universe does not begin from nothing. It moves from one state to another, but none of these proposals has yet been confirmed by observation. They are active areas of research, not established conclusions. The presence of the singularity also exposes a deeper issue. Our current physics is built from theories that work extraordinarily well in their own domains but resist unification. General relativity governs the large-scale structure of space-time. Quantum mechanics governs the small-scale behavior of matter and energy. Each is internally consistent. Together, they clash. The Big Bang singularity sits precisely at the intersection of these domains. It is the place where both theories must apply simultaneously, and where neither can operate alone. That is why it is such a persistent problem. It is not a flaw in cosmology alone. It is a symptom of a deeper fracture in our understanding of nature. This fracture has consequences beyond the technical. It affects how confident we can be in statements about the universe's origin. When popular explanations say that the universe began at a singularity, they're often compressing a complex situation into a misleading phrase. What they really mean is that our current models cannot describe earlier conditions reliably. This nuance is easy to lose. Singularities make for dramatic storytelling. They sound like definitive beginnings, sharp edges where everything starts. In reality, they are more like fog banks. You can sail toward them, charting your course with confidence until suddenly the landmarks vanish. Beyond that point, the map no longer helps. The limits of our physics also shape the debate about whether the Big Bang could be wrong. If the theory predicts a singularity and singularities are signs of failure, does that mean the theory is wrong? Not necessarily. It means the theory is incomplete. Most successful scientific theories are incomplete. Newtonian mechanics does not fail because it cannot describe black holes. It fails only when used outside its domain of validity. Within that domain, it remains extraordinarily useful. Similarly, the Big Bang model works extremely well for describing the universe after a certain early time. Its failure to describe earlier conditions does not negate its successes. This is a subtle point, but an important one. Scientific theories are not judged by whether they explain everything. They are judged by whether they explain something well, and whether they can be improved or replaced when they reach their limits. The singularity marks such a limit. It tells us where improvement is needed, not where everything collapses. There is also a psychological dimension to this discomfort. Singularities feel unsettling because they represent absolute limits. Humans tend to resist the idea that there are questions that cannot yet be answered. We prefer open doors to closed ones. The singularity looks like a closed door, but in science, closed doors often mark the boundary between one era of understanding and the next. They are invitations rather than conclusions. The fact that we can identify the problem so precisely is itself a sign of progress. It is also worth noting that the singularity problem is not unique to the Big Bang. Black holes, as described by general relativity, also contain singularities. At their centers, densities and curvatures become infinite. Again, most physicists do not believe these infinities exist physically. They believe that quantum gravity effects intervene and change the picture. This parallel is important. If singularities in black holes are taken as signs of incomplete description rather than literal features, consistency suggests treating the Big Bang singularity the same way. In both cases, the theory points beyond itself. The limits of our physics are therefore not a failure of cosmology alone. They are part of a broader story about how knowledge advances. We build models that work, we discover where they fail, and we search for deeper frameworks that incorporate the old ones as approximations. As you listen to this, you may notice that the question has shifted. It is no longer simply whether the Big Bang is right or wrong. It is whether it is complete, and completeness is a much higher standard. Recognizing the problem of singularity reframes the entire discussion. It suggests that the Big Bang is best understood as a description of a phase in the universe's history, not as the final word on its origin. It suggests that whatever came before, or whatever replaces the singularity, lies in a regime we have not yet mastered. This does not diminish the achievements of modern cosmology. It places them in context. The universe's expansion, the cosmic microwave background, the formation of structure, all of these remain robustly explained. What remains uncertain is how far back those explanations can be trusted. This awareness becomes increasingly important when scientists examine observations that do not fit neatly into the standard picture, or when they propose alternative models. They are not rejecting the Big Bang out of hand, they are probing its limits. For a theory that has explained as much as the Big Bang framework has, it is easy to assume that the picture it paints must be smooth and complete. From a distance, it often looks that way. Expansion explains redshift. A hot early phase explains background radiation. Simple physics explains the abundance of light elements. When these successes are listed together, the impression is one of remarkable coherence. But when scientists look closely, not from a distance but up close, certain details begin to feel uneasy, not broken, not obviously wrong, but slightly misaligned. These are not dramatic contradictions that overthrow the entire framework. They are small tensions, persistent puzzles, places where observation and theory do not quite settle into the same shape. In science, these are often the most interesting places. One of the most discussed cracks in the picture involves the rate at which the universe is expanding today. This rate is known as the Hubble constant, and measuring it sounds at first like a straightforward task. Observe distant galaxies, determine how fast they are moving away, measure their distances and calculate the relationship. In practice, it turns out to be anything but simple. What makes this situation uncomfortable is not that the Hubble constant is hard to measure. It is that different methods of measuring it give different answers. When astronomers infer the expansion rate by looking at the cosmic microwave background and extrapolating forward using the standard cosmological model, they get one value. When they measure distances and motions of relatively nearby galaxies directly, they get another. The difference is not trivial. It is larger than the estimated uncertainties. It has persisted despite improved data and refined analysis. This discrepancy is known as the Hubble tension, and it has become one of the most closely watched issues in modern cosmology. There are several possible explanations. One is that one or more measurement methods contain subtle, unrecognized errors. Another is that the standard cosmological model is missing something, perhaps a new form of energy, or a modification to known physics. The uncomfortable part is that no explanation has yet resolved the tension cleanly. This does not mean the Big Bang theory is wrong, but it does suggest that the simple picture of expansion may be incomplete. If the universe's expansion history is not fully captured by current assumptions, then our reconstruction of its early behavior may need adjustment as well. Another area where observations raise quiet questions involves the large-scale structure of the universe. According to the standard model, matter clumped gradually over time. Small density fluctuations in the early universe grew under gravity, eventually forming galaxies, clusters, and filaments. On average, this process works well, Simulations based on the Big Bang framework reproduce many features of the observed cosmic web. Yet, when astronomers examine specific details, some structures appear unexpectedly large or unexpectedly organized. There are vast regions with fewer galaxies than expected, and immense alignments that seem unlikely under random initial conditions. Individually, these features may be statistical flukes. Collectively, they invite closer scrutiny. Cosmologists are careful here. The universe is large and rare patterns are bound to occur somewhere. The challenge is distinguishing between genuine anomalies and the natural extremes of a probabilistic distribution. Still, the fact that such questions continue to arise reminds us that the picture is not as clean as simple summaries suggest. The cosmic microwave background itself, often described as one of the Big Bang's strongest pillars, contains its own set of oddities. On large scales, the background radiation is remarkably uniform. On smaller scales, tiny fluctuations carry information about early density variations. This pattern fits theoretical expectations extremely well. But when scientists analyze the largest angular scales, subtle anomalies appear. Certain temperature variations seem aligned in ways that are difficult to explain. Some regions appear slightly colder or warmer than expected. The overall distribution is still consistent with a Big Bang origin, but these features have resisted simple explanation. Again, none of this amounts to a decisive refutation. The anomalies could be statistical accidents, artifacts of data processing, or remnants of foreground contamination, yet they persist across multiple datasets and analyses, enough to keep the conversation alive. Another crack in the picture comes from the nature of dark matter and dark energy. These components are not minor adjustments. According to the standard cosmological model, ordinary matter accounts for only a small fraction of the universe's total energy budget. The rest is attributed to dark matter, which influences structure formation, and dark energy, which drives accelerated expansion. These entities are not directly observed. Their existence is inferred from gravitational effects and cosmic dynamics. This inference is robust in the sense that something must be causing the observed behavior. But what that something is remains unknown. The uncomfortable aspect is not just that we do not know what dark matter and dark energy are, it is that the Big Bang framework relies on them heavily. Without dark matter, galaxies would not form as observed. Without dark energy, the expansion history would look very different. Some researchers have explored alternatives such as modifications to gravity itself. These ideas attempt to explain observations without invoking unseen components. So far, none has matched the success of the standard model across all scales, but their very existence reflects a sense that relying so heavily on unknown ingredients leaves the picture feeling provisional. There is also the issue of early structure formation. Observations have revealed massive galaxies and quasars existing earlier in cosmic history than some models predicted. Forming such objects requires time, matter, and efficient processes. Their early appearance suggests that structure formation may have proceeded faster or more efficiently than expected. Adjustments can be made to accommodate these observations. Parameters can be tuned, feedback processes can be revised, but each adjustment adds complexity. The core framework remains intact, yet the edges become more intricate. Another subtle tension involves the uniformity of the universe. Inflation was introduced to explain why distant regions of the universe share similar properties, despite appearing causally disconnected. Inflation works well in many respects, but it raises questions about its own initial conditions and dynamics. Different inflationary models predict slightly different patterns in the cosmic microwave background. As measurements become more precise, some models are favored over others. So far, no single inflationary scenario has emerged as uniquely compelling. The broad idea remains plausible, but its details remain unsettled. This uncertainty does not undermine the Big Bang itself, but it does weaken claims that the early universe is fully understood. The picture becomes layered, with well-supported features resting atop less certain foundations. There are also observational puzzles closer to home. Measurements of galaxy rotation curves and gravitational lensing reveal discrepancies between visible matter and gravitational effects. Dark matter accounts for these discrepancies within the standard model, but the exact distribution and behavior of dark matter remain uncertain. Some small-scale observations do not match predictions perfectly. For example, the number of small satellite galaxies around larger galaxies appears lower than expected in some simulations. This issue, known as the missing satellites problem, has been mitigated by improved modelling, but it illustrates how details can challenge assumptions. Taken together, these cracks do not form a single fault line. They are scattered, varied, and often subtle. Each has plausible explanations. None demands abandonment of the Big Bang framework, but they collectively suggest that the story is still being refined. In science, this is not unusual. Theories often work extremely well at a certain level while struggling at the margins. The margins are where progress happens. They are where new ideas are tested, where assumptions are questioned, and where deeper understanding can emerge. It is also important to distinguish between cracks in the Big Bang theory itself and cracks in the broader standard cosmological model. The Big Bang refers primarily to the hot, dense early phase and subsequent expansion. The standard model includes additional assumptions about matter content, dark energy, and inflation. Some tensions may point to modifications in those additions rather than to the core idea of expansion. Public discussions often blur this distinction. When people say the Big Bang is in trouble, they may be referring to issues with dark energy, inflation, or structure formation, rather than with the basic expansion history. Precision matters here, because different problems suggest different kinds of solutions. As you reflect on these observational tensions, you may notice a pattern. The Big Bang framework is rarely contradicted outright. Instead, it is surrounded by questions that push its boundaries. These questions do not shout, they whisper. They ask whether certain assumptions are as secure as we think, whether certain parameters are truly fundamental, and whether deeper principles remain hidden. This kind of situation can persist for a long time in science. Sometimes tensions resolve as data improves. Sometimes they accumulate until a conceptual shift becomes unavoidable. It is not always clear which path will be taken. For now, the Big Bang remains the best available description of the universe's early evolution. But it is not beyond challenge. Its success does not guarantee its completeness. The cracks in the picture remind us that understanding the universe is an ongoing process, not a finished achievement. When the standard picture of the universe reaches its edges, when expansion leads backward to a singularity and observation meets horizons it cannot cross, it is almost inevitable that alternative ideas begin to appear. These ideas do not usually arise from a desire to overturn everything that came before. More often, they grow out of an attempt to soften the sharpest limits of the existing framework, to replace abrupt boundaries with continuity, and to answer questions that refuse to go away. What unites many of these alternatives is a shared discomfort with the notion of an absolute beginning. Not because a beginning is philosophically unacceptable, but because the physics surrounding it feels incomplete. Singularities, infinities, and unexplained initial conditions are not endpoints scientists are usually content to accept. They are markers that something deeper may be waiting underneath. One broad family of ideas replaces the idea of a single beginning with the idea of a bounce. In these models, the universe does not emerge from nothing. Instead, it transitions from a previous state. The expansion we observe today is the aftermath of a contraction that came before. In a bouncing universe, cosmic history extends further back than the Big Bang. The universe may have been shrinking for a long time, becoming denser and hotter, until some mechanism halted the contraction and reversed it. That reversal, the bounce, takes the place of the singularity. The appeal of such models is straightforward. If the universe never reaches infinite density, then the singularity problem disappears. Instead of equations blowing up, physical processes intervene. Quantum effects, repulsive forces, or new states of matter prevent collapse beyond a certain point. Several versions of bouncing cosmologies exist. Some arise from loop quantum gravity, where space itself is quantized. In these models, there is a smallest possible unit of volume. Compression beyond that limit is impossible, so contraction naturally gives way to expansion. The universe rebounds not because of an explosion, but because the fabric of space resists further squeezing. Other bounce models emerge from modified gravity theories, where the equations governing space-time behave differently at high densities. In these scenarios, gravity may become repulsive under extreme conditions, halting collapse and initiating expansion. While these ideas are mathematically consistent within their own frameworks, they face significant challenges. One of the hardest is matching observational data successfully as the standard Big Bang model does. Any viable alternative must reproduce the cosmic microwave background, the distribution of galaxies, and the observed expansion history with comparable accuracy. Another difficulty involves entropy. If the universe contracts and then expands, what happens to disorder? In most physical processes, entropy increases. A contracting phase would need to manage entropy carefully to avoid contradictions with the observed low-entropy early universe. Some models address this by proposing that entropy is reset or diluted during the bounce. Others suggest that entropy behaves differently in cosmological contexts. Closely related to bouncing universes are cyclic models. In these pictures, the universe does not experience a single bounce, but many. Expansion follows contraction, which follows expansion, repeating over immense timescales. Each cycle may last trillions of years. The universe has no beginning and no end, only transitions. Cyclic cosmologies have a long history. Even before modern physics, some philosophers imagined an eternal universe that renews itself endlessly. Modern cyclic models attempt to ground this intuition in mathematics and observation. One influential version proposes that the universe undergoes phases dominated by different forms of energy. Expansion slows, reverses, contracts, and then bounces again. Another version, sometimes called conformal cyclic cosmology, suggests that the far future of one universe becomes mathematically equivalent to the Big Bang of the next. These models offer intriguing solutions to the beginning problem. If the universe has always existed in some form, then there is no need to explain why it suddenly appeared. The question shifts from origin to dynamics. Why does the universe cycle the way it does? What governs the transitions? However, cyclic models face their own obstacles. Maintaining consistency across cycles without accumulating inconsistencies is difficult. Small deviations can compound over time. Entropy again poses a major challenge. If disorder increases with each cycle, the universe should eventually reach a state where cycles are impossible. Some cyclic models attempt to avoid this by proposing mechanisms that reset entropy between cycles. Others argue that entropy behaves differently on cosmic scales. These ideas are still under active debate. Another broad alternative involves eternal cosmologies that do not rely on cycles or bounces, but on ongoing processes without a global beginning. In these models, the universe may be eternally inflating, constantly generating new regions that look like Big Bang universes from the inside. Eternal inflation is not a rejection of the Big Bang so much as an extension of inflationary theory. In this picture, inflation never completely ends everywhere. While it stops locally, producing regions like our observable universe, it continues elsewhere. Each region emerges with its own expansion history, physical properties, and apparent beginning. From within one such region, the universe appears to have begun with a hot, dense phase. From the broader perspective, that beginning is local rather than absolute. There is no single starting point for the entire cosmos. This idea naturally leads to multiverse scenarios. If many regions form under slightly different conditions, then physical constants may vary from one region to another. The universe we observe would be one realization among many. Eternal inflation has the advantage of arising from mechanisms already proposed to explain early universe behavior. It also provides a possible explanation for why physical constants appear finely tuned for complexity. In a multiverse, observers exist only in regions where conditions allow them to exist. At the same time, this framework raises serious questions about testability. If other regions of the multiverse are causally disconnected from us, how can their existence be confirmed or falsified? Some argue that indirect evidence may be possible. Others worry that the theory drifts too far from empirical grounding. There are also eternal models that do not rely on inflation. Some propose steady state-like universes where large-scale properties remain statistically constant over time, even though local regions evolve. These ideas differ from earlier steady-state theories by incorporating modern observations and avoiding continuous matter creation in its original form. What all these alternatives share is an attempt to replace a sharp beginning with a broader context. They aim to answer the question the Big Bang theory does not. What, if anything, lies beyond its starting point? It is important to notice that proposing alternatives does not mean discarding the evidence that supports the Big Bang. Most of these models still include a hot, dense, early phase resembling the Big Bang. They reinterpret it rather than deny it. The cosmic microwave background, light element abundances and large-scale structure still need explanation. In that sense, the Big Bang may survive as a description of a phase rather than an origin. The question becomes not whether the Big Bang happened, but what kind of event it was within a larger story. Critics of alternative models often point out that adding new structures, cycles, or universes increases complexity. Occam's razor, the principle that simpler explanations are preferable, is sometimes invoked. Why multiply universes or cosmic phases when a single beginning suffices? Supporters respond that simplicity is not the same as truth. A theory that hides unanswered questions behind a singularity may appear simple, but that simplicity may be deceptive. A more complex model that resolves deep inconsistencies may ultimately be more satisfying. Another consideration is how science progresses. New ideas often appear speculative at first. They struggle to compete with established frameworks. Over time, some gain support, others fade away. The presence of many alternatives does not mean the field is confused. It means it is actively exploring its boundaries. From a broader perspective, these alternative cosmologies remind us that the universe may be stranger than any single model suggests. Our current theories are shaped by available data, mathematical tools, and human intuition. They are not guaranteed to capture the full picture. As you listen, you might notice that these alternatives vary widely in tone. Some feel conservative, extending known physics gently. Others feel radical, reimagining time, space, and causality. This diversity reflects the depth of the problem. When questions reach the foundations of reality, many paths must be explored. None of these ideas has yet displaced the standard Big Bang framework. That framework remains the most successful description of the universe's early evolution. But the existence of serious, mathematically consistent alternatives shows that the story is not closed. This matters for the original question. If the Big Bang were a complete and final explanation, alternatives would be unnecessary. The fact that they continue to be developed suggests that cosmology is still searching for a deeper understanding. The universe may have bounced, it may cycle, it may have no beginning at all in the usual sense, or the Big Bang may turn out to be the true beginning, with a singularity resolved in ways we cannot yet imagine. At this stage, honesty requires admitting that we do not know. What we do know is that the Big Bang theory, as powerful as it is, does not exhaust the possibilities. It describes what we can see and model with confidence. Beyond that lies a landscape of ideas shaped by both caution and imagination. What if the universe is not only stranger in its past, but older than we think? What if the timeline itself is longer, more layered, or more ambiguous than the neat number we often hear repeated? When people talk about the age of the universe, they often speak with a surprising degree of confidence. Around 13.8 billion years, give or take a few tens of millions. It sounds precise, almost comforting, as though the universe has a clearly printed birth certificate tucked away somewhere in the cosmic archives. This number appears in textbooks, documentaries, articles, and casual conversations, usually without much hesitation. And yet, when you look closely at how that number is obtained, and what assumptions it rests upon, the certainty begins to soften. The age of the universe is not something we measure directly. It is something we infer. It is the result of models layered on top of observations, interpretations stacked on top of equations. Change the assumptions, even slightly, and the age can shift. This does not mean the number is meaningless. It means it is conditional. The commonly cited age of the universe comes from combining measurements of cosmic expansion with a specific cosmological model. In simple terms, astronomers observe how fast the universe is expanding today, and use that information, along with assumptions about how the expansion rate has changed over time, to calculate how long it would take to reach the current state from a much denser one. This is similar to estimating how long a car has been traveling based on its current speed and an assumed acceleration history. If you know how fast it is going now and how it sped up or slowed down along the way, you can estimate when the journey began. But if your assumptions about acceleration are off, even slightly, your estimate of the starting time will be too. In cosmology, those assumptions are encoded in the standard model, including the influence of dark matter, dark energy, and the overall geometry of space. The age of 13.8 billion years is not a raw observational fact. It is the age implied by this particular model fitting this particular set of data. One reason this matters is that there are independent ways of estimating cosmic age that do not always line up perfectly. Astronomers can estimate the ages of the oldest stars, the oldest star clusters, and the earliest galaxies. These objects act as cosmic clocks. If a star is 13 billion years old, the universe must be at least that old. For a long time, there were mild tensions between stellar age estimates and cosmological age estimates. At times, the oldest stars appeared to be almost as old as the universe itself, leaving very little room for error. Improvements in measurements and models have eased these tensions, but they have not eliminated uncertainty entirely. More recently, the tension surrounding the expansion rate of the universe has reopened questions about age. As discussed earlier, different methods of measuring the expansion rate yield different values. A faster expansion rate today implies a younger universe. A slower rate implies an older one. If the universe is expanding faster than the standard model predicts, then extrapolating backward leads to a shorter timeline. If it is expanding more slowly, the timeline stretches. The current disagreement between measurement methods therefore has direct implications for cosmic age. Some proposed solutions to this tension involve modifying the early expansion history of the universe. These modifications can subtly change the inferred age. In some scenarios, the universe could be older than the standard estimate, even while still matching most observations. There is also a deeper question hidden beneath these calculations. What does it even mean to say that the universe has an age? Age, as we usually understand it, assumes a beginning point. It assumes a clock that started ticking at a definite moment. But if the Big Bang was not an absolute beginning, but rather a transitional phase, then the age we calculate may only apply to the current expansion phase, not to the universe as a whole. In bouncing or cyclic models, for example, the universe could be vastly older than 13.8 billion years. The expansion we observe would represent only the most recent cycle or rebound. From our perspective, looking backward, everything appears to originate from a hot, dense state. But that state would not be the first. In such a scenario, asking for the age of the universe is like asking for the age of a wave on the ocean. The wave has a beginning and an end, but the ocean itself does not begin with that wave. The age we measure belongs to the pattern, not to the underlying system. Even within inflationary models, similar ambiguities arise. If inflation is eternal to the past, or if it operates within a broader timeless framework, then the Big Bang-like phase we observe may not mark the beginning of all existence. It may mark the beginning of our observable region's history. In that case, the universe could be effectively older than any age we can assign using current observations. The number 13.8 billion years would describe the time since our region emerged from inflation into a hot, expanding phase, not the age of the entire cosmos. There is also the possibility that time itself behaves differently at very early stages. Some approaches to quantum gravity suggest that time may emerge gradually, rather than existing fully formed from the outset. If this is the case, then the concept of age becomes fuzzy near the beginning. If time emerges from more fundamental processes, asking how old the universe is may be like asking how old a shadow is relative to the object casting it. The question may have meaning only after certain conditions are met. These ideas are speculative, but they illustrate an important point. The age of the universe is not a single, unquestionable fact. It is a model-dependent quantity, meaningful within a particular framework and less so outside it. This becomes especially relevant when people ask whether the Big Bang could be wrong. Often, what they mean is not that the universe was never hot and dense, but that the timeline we associate with that phase may not represent the full story. The universe could have a deeper past that the Big Bang model does not capture. Another way the universe could be older than we think involves changes to early expansion dynamics. If the expansion history was more complex than assumed, perhaps involving additional phases or transitions, then backward extrapolation using a simplified model could underestimate the true duration. Even small deviations in early behavior can have large effects on inferred age. Because the timeline is compressed near the beginning, uncertainties there propagate forward dramatically. Observationally, probing these early phases is extremely difficult. The cosmic microwave background provides a snapshot of the universe when it was about 380,000 years old. Everything before that is inferred indirectly. While those inferences are grounded in well-tested physics, They are still extrapolations. This is not a flaw unique to cosmology. In geology, the age of the Earth is inferred using radioactive decay models. In biology, evolutionary timelines are inferred from genetic divergence. In each case, the estimates are robust but conditional. They depend on assumptions about processes over time. Cosmology operates under even more extreme conditions, dealing with energies and scales far beyond anything we can reproduce experimentally. That makes humility especially important. It is also worth noticing how language shapes perception here. Saying the universe is 13.8 billion years old sounds definitive. Saying the observable universe has been expanding for approximately 13.8 billion years under the assumptions of the standard cosmological model sounds less catchy, but far more accurate. Public discourse tends to favor the first phrasing. Scientific discourse prefers the second. The gap between them can create confusion, especially when new data challenge existing assumptions. None of this means that the universe is definitely older than we think. It means that the age we assign is provisional. It reflects our best current understanding, not an absolute truth guaranteed to survive future discoveries unchanged. As our measurements improve and our theories evolve, the number may shift. It may increase slightly, it may decrease slightly, or it may turn out that the question itself needs to be reframed. For listeners, this realization can be strangely calming. It removes the pressure to treat cosmological numbers as sacred. It invites curiosity rather than anxiety. The universe does not become less impressive if it is older, younger, or more complex than we imagine. If anything, it becomes more interesting. There is a quiet but important shift that happens when a question is framed slightly differently. Instead of asking whether the Big Bang is right or wrong, the focus turns toward whether it is finished. That change may sound subtle, but it reshapes the entire conversation. Wrong suggests failure. Incomplete suggests work in progress. Science, almost by definition, lives far more comfortably with the second than the first. To see why this distinction matters, it helps to step back and consider how scientific theories actually function. A theory in science is not a declaration of ultimate truth. It is a structured way of organizing observations, making predictions, and connecting disparate facts into a coherent picture. Theories are judged not by whether they answer every conceivable question, but by whether they explain what they claim to explain within a clearly defined domain. By that standard, the Big Bang theory has been remarkably successful. It explains why distant galaxies are receding from one another. It explains why the universe was hotter and denser in the past. It explains the presence and properties of the cosmic microwave background. It explains the relative abundance of the lightest elements. These are not minor achievements. They cover the large-scale behavior of the universe over billions of years. Yet none of these successes require the Big Bang to be a complete description of cosmic history. They require it only to be an accurate description of a particular phase. Confusion arises when that phase is treated as the entire story, rather than as one chapter within a larger unfinished framework. The idea of incompleteness is not an insult in physics. It is an expectation. Newtonian mechanics is incomplete. It cannot describe relativistic speeds or quantum effects. That does not make it wrong in everyday contexts. It makes it limited. Quantum mechanics is incomplete. It does not incorporate gravity. General relativity is incomplete. It does not include quantum uncertainty. Each theory remains indispensable within its proper scope. In this light, asking whether the Big Bang is incomplete is almost redundant. Of course it is. The more interesting question is where that incompleteness lies and what it tells us about the structure of reality. One place where incompleteness becomes obvious is at the earliest times. The Big Bang model describes how the universe evolves from a hot, dense state onward. It does not provide a well-defined account of how that state arose. The appearance of a singularity marks a breakdown, not a conclusion. That alone is enough to say the theory is not complete in the deepest sense. Another place where incompleteness shows itself is in the reliance on unknown components. Dark matter and dark energy are not minor footnotes. Together they dominate the universe's energy budget. Their existence is inferred from strong evidence, but their nature remains mysterious. A theory that depends so heavily on entities it cannot yet explain is, by definition, provisional. This does not mean dark matter and dark energy are imaginary. it means that our description of the universe is missing key pieces. Whether those pieces will turn out to be new particles, new fields, or modifications of existing laws is still an open question. The same can be said of inflation. Inflation solves several important problems in early universe cosmology, but it introduces its own unanswered questions. What drove inflation? Why did it last as long as it did? Why did it end in the way that produced our observed universe? Inflation works as an effective description, but its underlying mechanism remains uncertain. These gaps do not undermine the Big Bang. They surround it. Another reason the theory feels incomplete is that it treats certain conditions as given rather than explained. The initial uniformity of the universe, the specific spectrum of fluctuations, the low entropy at early times, all are inputs rather than outputs. The theory accepts them and shows how they evolve, but it does not explain why they were that way to begin with. This is often where philosophical discomfort creeps in. Why these laws? Why these constants? Why these initial conditions? The Big Bang model does not pretend to answer such questions. They lie outside its design. Expecting it to do so is like expecting a map to explain why the terrain exists. In public discourse, incompleteness is often mistaken for weakness. There is an assumption that if the theory does not answer everything, it must be on shaky ground. In science, the opposite is often true. Theories that clearly mark their limits tend to be the most robust. They invite refinement rather than collapse. This perspective also helps clarify why alternatives to the Big Bang are not necessarily competitors in the usual sense. Many alternative cosmologies retain the Big Bang as a phase within a broader structure. They do not discard its successes, they reinterpret them. For example, in a bouncing universe, the Big Bang corresponds to the transition from contraction to expansion. In eternal inflation, it marks the local beginning of our observable region. In cyclic models, it represents one turn of a much larger cosmic process. In each case, the Big Bang is incomplete, but not wrong. This reframing changes the emotional tone of the discussion. Instead of defending the Big Bang against every criticism, scientists can ask which parts of it are likely to survive deeper theories and which parts may be revised or replaced. History suggests that the broad idea of expansion from a hotter past is likely to endure, even if the details of the earliest moments change significantly. Another way to think about incompleteness is to ask how the Big Bang would look if discovered today for the first time. Would it be presented as a final explanation, or as a highly successful model with known limitations? Almost certainly the latter. Much of the confusion arises from how the theory has been communicated over time, not from what it actually claims. The word beginning carries heavy baggage. It suggests finality, absoluteness, and closure. In practice, the Big Bang describes a boundary of applicability, not a metaphysical origin. Treating it as incomplete rather than wrong aligns better with how physicists actually use it. There is also a deeper lesson here about how science handles ultimate questions. Some questions may not have answers in the form we expect. Asking what caused the Big Bang may presuppose a type of explanation that physics is not equipped to provide. Causation, as we experience it, depends on time. If time itself emerges from deeper processes, then causal language may need to be rethought. This does not mean the question is meaningless. It means the answer may not resemble ordinary explanations. Recognizing incompleteness allows space for that possibility without forcing premature conclusions. It is also worth noticing how often scientific revolutions involve reframing rather than rejection. Relativity did not declare Newton completely wrong. It showed that Newton's laws were approximations valid under certain conditions. Quantum mechanics did not erase classical physics. It explained why classical behavior emerges from deeper rules. In that sense, whatever replaces or extends the Big Bang is likely to include it as a limiting case. The expansion history, the cosmic background radiation, the growth of structure, these features are unlikely to vanish from future theories. They're too well supported by evidence. What may change is how those features are embedded in a larger picture. The earliest moments may be described differently. Time may behave differently. Space itself may have a discrete structure. The notion of a beginning may dissolve into something less absolute. Seeing the Big Bang as incomplete also helps diffuse the idea that questioning it is somehow anti-scientific. On the contrary, probing incompleteness is how science advances. Every major breakthrough has emerged from identifying where existing theories stop working smoothly. This perspective encourages a quieter, more patient kind of curiosity. Instead of demanding final answers, it allows questions to remain open. Instead of framing uncertainty as failure, it treats it as a guide. As you listen to this, you may notice that the universe feels no less real or stable when its description is incomplete. In fact, it may feel more alive, more dynamic, more open to discovery. A finished universe is static. An unfinished one invites exploration. The Big Bang, then, can be understood as a remarkably successful description of a vast stretch of cosmic history, paired with a clear acknowledgement of its limits. It tells us how the universe expanded, cooled, and structured itself. It does not tell us everything about why or from what deeper processes those events emerged. Holding this balance is not easy, especially in a culture that prefers definitive answers, but it is closer to how science actually operates, moving forward through approximation, revision, and deepening insight. With that shift in perspective, the next question naturally arises. If scientific theories are allowed to be incomplete without being discarded, how do they change over time without everything falling apart? Stability is not usually the first word that comes to mind when people imagine scientific change. The popular image is far more dramatic. Old ideas collapse, new ones sweep in, textbooks are rewritten overnight. Everything we thought we knew turns out to be wrong. It is a compelling picture, but it bears very little resemblance to how science actually evolves, especially in fields like cosmology, where theories are built slowly, tested indirectly, and refined across generations. Understanding how scientific theories change without everything falling apart is essential for making sense of the ongoing conversation about the Big Bang. Without that understanding, any revision can feel like a threat, any uncertainty like a crack in the foundation. With it, change looks less like destruction and more like careful renovation. At the heart of this process is a simple but often misunderstood idea. Scientific theories are not fragile structures held together by belief. They are resilient frameworks anchored by evidence. When they change, they rarely shatter. They bend, stretch, and absorb new information, sometimes transforming in shape while retaining their core function. A useful place to begin is with how theories are built in the first place. A scientific theory does not emerge fully formed. It grows from patterns observed in data, from regularities that demand explanation. Early versions are often rough, incomplete, and limited in scope. Over time, as measurements improve and new phenomena are discovered, the theory is adjusted to accommodate them. This adjustment process is not arbitrary. It is constrained by what already works. A theory that successfully explains a wide range of observations cannot simply be discarded without replacing those explanations. Any new theory must either reproduce the old theory's successes or explain why those successes appear to hold under certain conditions. This is why scientific revolutions are usually additive rather than subtractive. When relativity replaced Newtonian gravity, it did not invalidate Newton's laws in everyday situations. It explained why Newton's laws work so well at low speeds and weak gravitational fields, while revealing their limitations at extreme scales. Engineers still use Newtonian physics every day. Its domain did not disappear, it was clarified. The same pattern appears in quantum mechanics. Classical physics did not become useless when quantum theory arrived. It became understood as an approximation that emerges from deeper rules when systems are large and energies are moderate. The world did not fall apart. It became layered. Cosmology follows this same pattern. The Big Bang theory did not emerge by destroying earlier astronomy. It built on it. Observations of stars, galaxies, and motion remained valid. What changed was the interpretation of large-scale structure and history. When people worry that questioning the Big Bang might cause everything to collapse, they're often imagining science as a single rigid story. In reality, it is a collection of interconnected models, each with its own range of validity. Changing one part does not automatically destabilize the rest. This resilience comes from redundancy. The Big Bang framework is supported by multiple independent lines of evidence. Expansion is seen in galaxy redshifts. Early heat is recorded in background radiation. Nuclear processes are reflected in elemental abundances. These facts do not vanish if the theory is refined. They must be explained by whatever framework replaces or extends it. Because of this, scientific change is usually conservative in the best sense of the word. It preserves what works. It modifies what does not. It rarely starts from zero. Another important aspect of stability is the role of uncertainty. Contrary to popular belief, uncertainty does not weaken a theory. Unacknowledged uncertainty does. When scientists explicitly identify the limits of a model, they create space for growth without crisis. The Big Bang Theory includes such limits. It does not claim to describe the universe at all times and scales. It does not claim to explain the ultimate origin of physical law. These omissions are not flaws, they are boundaries. When new observations press against those boundaries, scientists do not panic. They ask whether the boundary can be pushed outward, or whether a deeper framework is needed. This mindset prevents collapse because it anticipates incompleteness from the beginning. Another stabilizing factor is the way theories are embedded in practice. Cosmology is not just a set of ideas. It is a working discipline. Observations are planned, instruments are built, data are analyzed, and predictions are tested. A theory that works well in practice acquires a kind of inertia. It is not easily displaced by speculation alone. This is why alternative cosmologies, no matter how elegant, must do more than propose new narratives. They must match the predictive power of the existing framework. They must account for the same data at least as well. Until they do, the standard model remains in place, even if it is known to be incomplete. The process resembles architectural engineering more than demolition. You do not tear down a bridge because you discover that its design can be improved. You reinforce it, adjust it, and sometimes rebuild sections while keeping it operational. There is also an important social dimension to scientific stability. Science is not done by isolated individuals working in conceptual vacuum. It is done by communities that share methods, standards, and expectations. These communities change slowly, not because they resist truth, but because coordination matters. A radical change must be communicated, tested, debated, and reproduced across many independent groups. This takes time. During that time, old and new ideas coexist. This coexistence can look messy from the outside, but it is part of what keeps science grounded. This gradualism is often misinterpreted as stubbornness. In reality, it is caution. Extraordinary claims require extraordinary evidence, not because scientists are dogmatic, but because they are responsible for maintaining coherence across vast bodies of knowledge. Another reason theories do not fall apart easily is that they are modular. Different components address different questions. In cosmology, expansion history, structure formation, particle physics, and gravity are related but not identical domains. Adjusting one does not require rewriting all the others. For example, revising our understanding of dark energy does not invalidate stellar evolution models. Modifying inflationary theory does not change how light travels through space today. This compartmentalization allows progress to occur locally without global collapse. It also allows theories to be tested incrementally. Predictions can be refined, parameters can be adjusted, new observations can be incorporated. At no point is everything on the table at once. This is why the idea of the Big Bang being incomplete does not alarm cosmologists. It is expected. What would be alarming is a theory that claimed to explain everything perfectly, leaving no room for further inquiry. In fact, the history of science suggests that theories which appear too complete often hide unresolved assumptions. These assumptions eventually surface as contradictions or anomalies. A theory that openly acknowledges its limits is healthier. This perspective also helps explain why public debates about science can feel more dramatic than professional ones. Outside the scientific community, theories are often treated as beliefs rather than tools. Changing a belief feels like losing ground. Refining a tool feels like progress. When people hear that cosmologists are questioning aspects of the Big Bang, they may imagine chaos. Inside the field, it feels more like routine maintenance. The universe has not become unstable because our descriptions evolve. The universe does not care what we think about it. Our models change because they are approximations, not because reality is fragile. There is also an emotional element worth acknowledging. Humans prefer certainty, especially about fundamental questions. Knowing how everything began feels grounding. When that knowledge becomes provisional, it can feel unsettling. Science does not exist to provide comfort. It exists to describe reality as accurately as possible, even when that description resists closure. Learning to live with provisional understanding is part of engaging honestly with science. This does not mean anything goes. Constraints matter, evidence matters, mathematical consistency matters. Theories do not drift aimlessly. They are guided by what the universe reveals through observation and experiment. In cosmology, this guidance is especially indirect. We cannot recreate early universe conditions in laboratories. We infer them from faint signals and distant light. This makes caution even more important. As a result, changing cosmology is often slower and more conservative than in other fields. When change does occur, it tends to be carefully justified. Seen from this angle, the ongoing discussion about the Big Bang looks less like a crisis and more like a maturation. The theory has moved beyond its early triumphs into a phase where refinement and integration with deeper physics are required. This is a natural stage in the life of a successful theory. Early success establishes credibility. Later challenges expose limits. Those limits motivate deeper work. The Big Bang theory is currently in this second phase. Its core insights remain robust. Its boundaries are increasingly visible. That visibility is a sign of progress, not decay. As you reflect on this, it may help to release the idea that science advances through sudden revelations. Most of the time, it advances through careful adjustment, patient debate, and incremental insight. Theories change without everything falling apart because they are designed to. They are provisional by nature. They are built to be revised. This understanding sets the stage for the final shift in perspective. If the Big Bang is incomplete rather than wrong, and if scientific theories evolve without collapsing, then the real question becomes less about error and more about meaning. What does it mean for us, as observers inside the universe, to live with an origin story that is still unfinished? How does that uncertainty shape our place in the cosmos, not as a problem to be solved, but as a condition to be lived with? Somewhere beneath the equations, the observations, and the careful language of cosmology, there is a quieter question that tends to surface only after the technical debates have settled for a moment. It is not a question about expansion rates or background radiation. It is a question about perspective. If the beginning of the universe is not as clean, singular, or final as we once imagined, what does that actually change for us? At first glance, the answer might seem to be very little. Stars still burn, galaxies still drift, time still moves forward in the way we experience it. Our daily lives do not depend on whether the universe began with a singular event, a bounce, or something else entirely. And yet, when ideas about origin shift, they tend to ripple outward in subtle ways. They affect how we think about time, meaning, certainty, and our place within something vastly larger than ourselves. For a long time, the Big Bang has served as a kind of cosmic anchor. It offered a definite starting point, a moment where the story began. Even for those who did not think about it often, that beginning sat quietly in the background, giving the universe a clear direction. There was a past that led to a present, and the present moved away from a known origin. If that origin turns out to be less absolute, less final, or less singular than we thought, the anchor loosens. The universe begins to look less like a story with a first page and more like a process whose edges are harder to define. This does not remove meaning, but it changes its texture. One of the first things this shift affects is how we think about time. A universe with a sharp beginning invites us to imagine time as something that started ticking at a particular moment. Everything after that moment counts. Everything before it does not exist. This aligns neatly with how we tell stories, mark anniversaries, and measure age. If instead the Big Bang marks a transition rather than a creation, time becomes more layered. The time we measure, the time recorded in clocks and calendars, may belong only to a particular phase of cosmic history. There could be forms of time that preceded it, or structures where time behaves differently altogether. For us, this does not mean our experience of time is invalid. It means our experience is local. We live within a particular slice of cosmic history, shaped by specific physical conditions. Our clocks measure the rhythm of this slice, not necessarily the rhythm of all existence. There is something humbling in that realization. It suggests that even our most basic intuitions, like before and after, may not be universal truths, but context-dependent tools that work well within our environment. This humility extends to the idea of certainty. A clean beginning encourages the belief that the universe is, in principle, fully knowable. If we can trace everything back to a starting point, then perhaps, given enough data and computation, the entire story can be reconstructed. When the beginning becomes fuzzy, that sense of total knowability softens. There may be aspects of cosmic history that are fundamentally inaccessible, not because we have failed to discover them, but because the universe itself does not preserve that information in a retrievable way. This can feel unsettling, especially in a culture that often treats knowledge as something that accumulates endlessly. But it can also be freeing. It allows us to accept mystery without treating it as a flaw. For us as individuals, this shift can subtly change how we relate to science. Science becomes less about delivering final answers and more about mapping reliable regions within a vast unknown. The value lies not in closure, but in clarity about where clarity is possible. Another implication touches on meaning itself. When the universe is framed as having a definite beginning, it is tempting to attach significance to that moment. Origins feel important. They feel purposeful, even when described in purely physical terms. If the universe did not begin in a single decisive event, then meaning does not cluster at the start. It emerges gradually, locally, through processes rather than through a single act. Stars form, planets coalesce, life appears, consciousness arises, meaning unfolds rather than being planted at the beginning. This view aligns well with what we observe. Meaning, as we experience it, is not something handed down from the start of time. It is something constructed through relationships, memory, and awareness. A universe without a sharp beginning does not diminish that process. If anything, it emphasizes it. There is also a shift in how we think about ourselves as observers. In a universe with a clear beginning, it is tempting to imagine ourselves as late arrivals, appearing near the end of a long predetermined sequence. Everything important happened early. We are living in the aftermath. If the universe is older, cyclic, or eternal in some sense, that framing changes. We are not late to the story. We are participants in an ongoing process that does not privilege one moment over another. This does not make us more important in a cosmic sense, but it does make our moment less derivative. We are not simply living in the fading echo of an initial event. We are embedded in a living, evolving structure that continues to generate novelty. This perspective can influence how we think about the future as well. A universe that began suddenly and is heading towards some final state can feel finite in a narrative sense. There is a beginning, and there will be an end. Our role lies somewhere in between. A universe without a clear beginning invites different kinds of futures. Cycles suggest renewal, eternal processes suggest continuity. Even scenarios involving eventual heat death take on a different tone when the past is not anchored to a single origin. For us, this can subtly affect how we think about progress, legacy, and continuity. Our actions do not sit between two absolute endpoints. They are part of a much longer, less sharply bounded flow. There is also an emotional dimension to this. Humans often look to beginnings for reassurance. Knowing where something came from can make it feel less arbitrary. When beginnings blur, the universe can feel less like a designed system and more like an emergent one. Some people find this unsettling. Others find it comforting. An emergent universe does not impose meaning from the top down. It allows meaning to arise where conditions allow it, including here, in conscious beings capable of reflection. This does not require abandoning awe. If anything, it deepens it. A universe that continually generates structure without a single starting command is, in its own way, more remarkable than one that began with a single decisive act. It is also worth considering how this shift affects our relationship to uncertainty. If the beginning is not fully known, and perhaps not fully knowable, then uncertainty becomes a permanent feature rather than a temporary inconvenience. Learning to live with that uncertainty is part of scientific maturity. It mirrors personal maturity as well. We do not demand complete certainty in our relationships, our identities, or our futures. We learn to navigate complexity without final answers. In this sense, cosmology becomes a mirror. How we respond to uncertainty about the universe often reflects how we respond to uncertainty in our own lives. Do we see it as a threat or as an invitation to curiosity? Another implication lies in how we teach and communicate science. If the Big Bang is incomplete rather than wrong, then science education benefits from emphasizing process over proclamation. Students learn not just what we think we know, but how that knowledge is structured, tested, and revised. This approach builds resilience. It prepares people to encounter new information without feeling that everything they learned before has been invalidated. It fosters trust in science as a method rather than as a source of final answers. For those listening quietly, perhaps late at night, these ideas do not demand action. They do not require you to change how you live tomorrow. They simply offer a different backdrop against which everyday life unfolds. You still wake up. You still rest. You still notice time passing. The universe still expands, whatever that ultimately means. The difference lies in how rigidly we hold the story of where it all began. If the beginning is not what we thought, then our place in the universe is not diminished. It is contextualized. We are part of a story that is larger, older, and less neatly packaged than we once imagined. There is something gently reassuring in that. It means we are not responsible for understanding everything. We are participants in a process that continues whether or not we have the full map. If the universe resists a single, definitive origin story, and if our theories remain open-ended, what does it mean to arrive at the end of this exploration, knowing that the story itself may never truly end? Quietly, without announcing itself, a realization tends to settle in by the time we reach the edge of this conversation. The universe we inhabit is not a solved puzzle. It is not a finished diagram with every piece locked into place. It is a system still holding back information, not out of secrecy or indifference, but because of the way it is structured, layered, and lived inside. Living inside a universe that is still keeping secrets is not a failure of science, and it is not a personal shortcoming on our part. It is a condition, one we've always lived with, even when we believed otherwise. For much of human history, the night sky felt unknowable in a very different way. Stars were distant lights with no clear explanation. Motion in the heavens was mysterious, and often interpreted through stories rather than measurements. Over time, careful observation replaced myth, and patterns replaced speculation. We learned that stars are suns, that galaxies exist beyond our own, that the universe expands. Each step forward made the cosmos feel more intelligible, and yet, with each layer of understanding, new forms of mystery appeared. The Big Bang once felt like a final answer, a moment where everything began, neat and definitive. Over time, that confidence softened. The beginning became less like a point and more like a boundary, then less like a boundary and more like a region of uncertainty. Now it feels increasingly like a question we have learned how to ask clearly, without yet knowing what a full answer would even look like. This does not mean progress has stalled. It means progress has changed its character. When you live inside a universe that still keeps secrets, knowledge becomes something other than conquest. It becomes navigation. You learn where the ground is solid and where it thins. You learn which questions lead to reliable answers and which ones lead to deeper questions instead. This kind of knowledge is quieter. It does not declare victory. It does not rush to closure. It moves carefully, aware that the map is always provisional. There is something deeply human about this shift, even though it unfolds at cosmic scales. In everyday life, certainty tends to shrink as understanding grows. Children want clear rules. Adults learn that context matters. Wisdom often involves knowing where answers stop being sharp. Cosmology, at its current stage, reflects that same maturity. The universe's secrets are not hidden behind a locked door we have yet to open. Many of them lie in regions where our usual concepts stop working smoothly. Time, cause, beginning, and even existence itself become less cooperative the closer we push toward extremes. That resistance is not hostility. It is structure. A universe that allows observers like us to exist is already performing an extraordinary balancing act. It operates across scales that dwarf intuition. It contains processes that unfold over billions of years and others that flash by in fractions of a second. It permits patterns stable enough to support life, yet dynamic enough to keep changing. Expecting such a system to reveal all of its foundations cleanly may be asking too much of any single framework. Instead, what we see emerging is a layered understanding. At one layer, the universe expands from a hotter past. At another, space and time behave according to relativistic geometry. At another, quantum rules dominate. At still deeper layers, we suspect connections that remain mathematically incomplete. None of these layers cancel the others, they coexist. Living inside this structure means accepting that some explanations work locally rather than globally. The Big Bang works exceptionally well as a description of our universe's expansion history. It may not describe the full architecture of reality. Both of those statements can be true at the same time. This realization can change how science feels emotionally. Instead of being a ladder that climbs toward final truth, it becomes more like a shoreline that gradually extends. Each step forward reveals more coastline, not less ocean. For many people, this is surprisingly calming. There is no pressure to arrive at the final answer. There is no obligation to resolve the deepest mysteries before resting. The universe is not waiting for us to finish understanding it in order to function. We are allowed to be partial observers. This matters especially when thinking about our own place in the cosmos. For a long time, humans struggled with the idea that we are not central. Earth is not the center of the solar system. The sun is not the center of the galaxy. The galaxy is not the center of the universe. Letting go of centrality was difficult, but it did not erase meaning. It relocated it. Letting go of a definitive cosmic beginning follows a similar pattern. Meaning does not vanish when origins become uncertain. It relocates from the start of the universe to the processes unfolding within it. Meaning becomes something that arises rather than something that was assigned. This has practical consequences for how we think about knowledge itself. If the universe keeps secrets, then humility becomes a strength rather than a weakness. Curiosity becomes more valuable than certainty. Patience becomes part of understanding. These qualities are not often celebrated in dramatic science narratives, but they are central to real scientific practice. They also align well with the experience of listening quietly, letting ideas pass without needing to resolve them immediately. You do not need to remember every detail. You do not need to decide which model is correct. You're allowed to simply notice how the question feels. Does the universe feel more open when its beginning is less rigid? Does it feel less threatening when uncertainty is acknowledged rather than denied?